Alright, these are the problems for the part 2 of our Skill 6 review. It's asking us here to rewrite the following exponential equation as a logarithmic equation. Okay, so we have a log, and we want to identify the base for this equation, and the base is 2. The argument is 256, and the exponent, a logarithm equals an exponent, and that is 8. So it's very pattern oriented. That's all you have to do for that problem. Alright, here rewrite the logarithmic equation as an exponential equation. So you're just going in the reverse order. Log base 6 of 1 over 36 is equal to negative 2. 6 is the base. This base has an exponent associated with it, and the logarithm always equals the exponent. So 6 to the negative second power is equal to 1 over 36 is the exponential equation. So this is the log equation. This is the exponential equation. Alright, rewrite the following logarithmic equations as exponential equations and determine the value of x. They want us to solve for x here. Alright, the base is 5. A logarithm equals an exponent. So we have 5 to the 4th power is equal to x, or x is equal to 625, I believe. So here it's same directions. Log base 3 of 1 over 27 is equal to x. The base is 3. The logarithm equals the exponent, equals 1 over 27. Now, sometimes when we have exponential equations, we can solve them by rewriting each side with the same base. So let's try to do that here. I know that 27 is 3 to the 3rd power. Now, I also know that this means 1/3 times 1/3 times 1/3. I can rewrite this 1 over 3 to the 3rd power as 1/3 raised to the power of 3. Alright, now the base on the left hand side is 3, but the base on the right hand side is 1/3. I can rewrite this base of 1/3, I can write it as 3 if I change the sign of the exponent. So now we come up to a property that students may not be aware of, that exponential functions and log functions are what they refer to as one-to-one functions. With one-to-one functions, the graph of your function, first it'll pass a vertical line test because it's a function, and then next it'll pass a horizontal line test. What that implies is that if these two numbers are the same and the base is the same, the exponents must be the same. X is therefore equal to negative 3. Now, I know that students say that the 3's cancel, and technically that is incorrect. So if you want to describe it using correct mathematical vocabulary, the justification is that they are one-to-one functions. Alright, so here we have a similar problem. We've got this base of x. The logarithm equals the exponent. On the right hand side, we've got 1/8. Okay, so let's see if we could this time. Let's see if we can write this 1/8 with an exponent of negative 3. Let's 1 over 8 is 1 over 2 cubed, and I can write this again. This means 1/2 times 1/2 times 1/2. If we flip the fraction, we've got to change the sign of the exponent. So again, because this is 1 to 1, if the numbers are the same and the exponents are the same, the base must be the same. So this x must be the 2 divided by 1, and 2 divided by 1 is just 2. Alright, now here we have to use our calculator, and you will be given the that little reference sheet that has the properties of logarithms. I won't take that away, I'll still provide that. So on the bottom of that reference sheet, if you recall, we have what is referred to as the change of base property. And that change of base property is extremely nice when you're using a calculator, a scientific calculator. Your calculator only has 2 log buttons. It has a common logarithm that's base 10 and a natural logarithm that's base e. The common log button, it just says log on your calculator, but the natural log button says ln. Alright, this change of base formula, if you have log base b of a, you can key this in on your calculator even though your calculator doesn't have a base b button. You can write that, key that in as the common log of a divided by the common log of that base b. Now, if you had a preference, you could use the natural log button as well. So this ratio is the same thing as the natural log of a divided by the natural log of b. Alright. So this number 22 is just an application of using this change of base. I accidentally hit that not equal right there. Alright, let's shrink this. Okay, so log base 4 of 60, I don't have a base 4 button on my calculator, but by this change of base formula, I can take the common log of 60 divided by the common log of 4. It wants me to give it to 3 decimal places, and I can fix my calculator to round for me so I don't make a silly round off error. And if I have, when you key in the log, do not forget to close the parenthesis after the 60, and what I get is 2.953. So check and see if that you get the same. You don't want to miss this problem, it's just a calculator problem. Alright, same thing here. We have the log of 4, and you know what, let's do natural log just to point out that it doesn't matter which button we use. If I use the natural log of 4 divided by the natural, now I can't mix and match. I can't use natural log on top and common log on, you know, the bases have to be the same. This is base E, this is base E. Alright, so again to 3 decimal places, and don't forget to close the parenthesis after the 4. I'm getting 0.667 to 3 decimals. I also just noticed that with this problem, I needed a calculator over here because 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64. You know, what this is telling us in that previous problem is that, and you can check this on your calculator, if you take this base of 4 and the logarithm equals an exponent, so this log equals this 2.953. Now, because of round off error, it's not going to be exactly 60, but this should be really close to 60 if this is a correct answer. We can check that on the calculator. Take 2.953 and raise it to, take 4 and raise it to the 2.953, and I'm getting to 3 decimals. I'm getting 59.963. If I would have carried this out more than 3 decimals, this number would get closer and closer to 60. Alright, now in this next problem, I notice that this 0.667 is most likely 2/3. Let's come over and see if there's an algebraic solution, see if that we can figure out what this is without a calculator. If I don't know what this is, let's just call it x. Okay, so the base is 8, a logarithm equals an exponent, and so I have 8 raised to the x power is equal to 4. Well, I notice that I can write each of these bases base 2. 8 is the same thing as 2 cubed. 4 is the same thing as 2 squared. When you have a power raised to a power, you multiply the exponents, and 3 times x is just written as 3x. So if the numbers are the same and the bases are the same, then because this is a one-to-one function, the exponents must be the same. Divide by 3, we get 2/3, which is repeating decimal 0.6, and to 3 decimals is 0.667. So for this one, I actually didn't need the change of base formula because my answer was, I could rewrite it and solve it with equating these same bases. But when you can't do that, you definitely need a scientific calculator, and the scientific calculator will always work. So this is probably the preferred solution. However, I just want you to recognize that. Alright, so here, if we go to the calculator, again, it doesn't matter whether we use a common log button or a natural log button. The log of 0.2 divided by the log of 3, and what do we have there? The log of 0.2, close the parentheses, divided by the log of 3, and I get negative 1.465. Use the laws of logarithms to simplify this expression. So we've got 4 properties to know. In the previous problem, we already talked about the change of base formula. So we have a rule that's called the product rule. If you have the log of a product, if you have the log of 10, you can break 10 down to 2 times 5, and then take the log of the first factor plus the log of the second factor. And this is called the product rule. Now remember that this equality, you can look at it the other way. You can say if I have 2 logarithms of the same base and I'm adding them together, I can condense that to a single logarithm if I take their product. Okay. So when they write it like this, like the top one, they expect you to understand that you can switch the sides. So there's also a quotient rule. If this is the product rule, and product just means multiplication, and quotient is that fancy word for division. If multiplication changed to addition, it's probably no surprise that the division is going to change to subtraction. Okay, and then we have what's called a power rule, that if you have an exponent, you can change this and move that exponent down out in front and change this to multiplication. So product rule, quotient rule, power rule. Those are the properties, as well as the change of base. And the change of base is most likely going to be used when the directions are referring you to use a calculator. Alright, we can write it down here just to be complete. If we have the log base b of a, then it's the log of a divided by the log of the base. And that's the change of base. Alright, so let's come over here. They want us to use these to simplify the expression, so in other words, to condense it. by the power rule, this 1/2, we can move that up as an exponent. So just where we have this and we can pull it down, if you have the multiplication in front, you can take that and move it up as an exponent as well. So to the 1/2 power. And remember that besides all of our properties of logarithms, we also are expected to remember our properties of exponents and also how radicals and stuff as well, that x raised to the m over n can be written in radical form. This denominator is the index of the radical, and here x to the m. So when you have x to the 1/2 power, that 2 is the index and x to the first. However, most of the time when you're writing radicals and you're talking about a square root, the 2 is implied, just like that exponent of 1 is implied, and they'll write the square root of x to the first power. They'll just write it radical x, and the 2 is implied. It's implied that it's a square root and not a cubed root. Alright, so now we have the addition of two logarithms. Both of these logarithms have the same base, and out in front their coefficients are 1. We couldn't over here our property doesn't have numbers other than 1 out in front. 1 is an implied coefficient, so this addition can be now written as multiplication, and I can multiply in any order. So most of the time, rather than x to the 1/2 times 9, you'll write the 9 first. And somebody may leave it like that, or somebody may choose to write x to the 1/2 and write it in radical form and write the square root. So either one of those answers would be acceptable. Alright, same directions, same situation. You're going to apply these properties, these laws of logarithms. Just like before, when we had the 1/2 out in front, we brought it up as an exponent. We've got this 5 out in front. We're going to bring it up as an exponent. So we have the log of x to the 5th power minus this log base 3 of y. Since we have the same base, we can write this as a single logarithm. Our quotient rule says subtraction, that this can be written as a division problem. Log of the numerator minus log of the denominator. My numerator is x to the 5th. My denominator is y. And I can't condense that any further, so I've simplified that as far as I can go. Now here, we're not using a scientific calculator, but we're just using substitution in these properties to try and evaluate what log base a of this 14 times a to the 4th is. So I see multiplication, 14 times a to the 4th, and I know that I can break that logarithm into two logarithms because it's the log 14 and then times a to the 4th. And I can write this like this. Okay. Now I come up to what's given, and I don't see a log of 14, but I do see 2 and 7. I do see that I can break this 14 up into 2 times 7. I've got 2 times 7. Now that's not 2.7. That dot means multiplication. And by the power rule, that 4 that's an exponent can come out in front as multiplication. The log of this product, I can take the log base a of the first factor, 2, plus the log of the second factor, 7. And remember, this logarithm equals an exponent. A raised to some power is equal to A. Well, this is just a fancy way to write the number 1. A to the first power is equal to 1. So this log base A of A, log base B of B, anytime that this base and this argument are the same, you're going to get 1, provided, of course, now the B, there is some restrictions on our base. It has to be positive, and they don't have it equal 1. All right. So I know that this guy is just 4 times 1. So I believe now I'm ready to substitute and find out what my final answer is. Log base A of 2 is given to me as 0.566. Log base A of 7 is given to me as 1.590. And I know that 4 times 1 is 4. So I can use my calculator and add these guys up. Just be careful not to make any keystroke errors. Alright, if I've keyed that in correctly, I get 6.156. Alright, I kept my calculator fixed to 3 decimals because all of these values that were given were at 3 decimals. Okay, same directions, different problem here, same idea. We have the log of a quotient. Well, this single log can be written as 2 logs because I can write it as log of the numerator minus the log of the denominator. Now I don't have log of 100, but I do have log of 10. Alright, and I know that 100 is 10 squared. And now, again here, A to what power is equal to A? Well, I know that this guy is just 1 in disguise. I know that this log base A of A is equal to 1. By the power rule, this exponent of 2 gets pulled down out in front. Try and write that better as a 2. You know, my A's and my 2's look similar. Now, this subtracting 1 is not part of the logarithm, so that's often why they use parentheses, just to help people read what they need there. Alright, so log base A of 10, well, I don't have that oh yeah, I do, right here. It's given to me as 1.881, then subtract 1. So now let's key this into a calculator. If I've keyed that in correctly, I'm getting 2.762. Alright. Log base A of 5. Now they're not giving me 5. And at first you're like, wait a minute, how am I going to get 5? Using the numbers they give me, 10 and 2, I can write 5 as 10 divided by 2. So it does take a little bit of playing around and maybe some scratch work to play with the numbers through multiplication or division to get the number that you wanted. And we wanted 5, so we got it from 10 and 2. So this is the log of the numerator minus the log of the denominator. And they give us both of these values. 1.881 minus there it is, 0.566, and when I do that subtraction, I get 2.315 if I've keep that in right. I used my calculator. Alright. Remember that we can rewrite exponents, rational exponents in radical form like this. Alright, so I know this is log base A of 10 raised to the 1/3 power. By the power rule, that 1/3 comes out in front as multiplication. And they give us the log base A of 10. So when I do that multiplication, I get 0.627. That's to 3 decimals. That's since they did these to 3 decimals, I'm giving my answer to 3 decimals. Alright, I believe that's it for the second part of the review. Let's double check. There it is. Yeah, that's the last problem. Alright, so good luck. Talk to you later. Bye.